Okay, hey guys, welcome. Today we will cover, well, this is elementary algebra 2, and we will cover complex numbers. We'll talk about induction. We're also going to talk about polynomials. Well, there's a lot of things to cover in polynomials, so okay, let's get started. I want to start a bit with things about complex numbers. Since I didn't have the chance to cover anything basically about complex numbers last time, although it was in my plan, but it's kind of hard for me to cover everything. So today we'll talk about, let's say, complex numbers a bit. Of course, I cannot cover everything about complex numbers, about induction. And when I talk about induction, I would like to say induction in algebra so that it's specific. And at the end, we'll be covering polynomials. So that's the plan for today. Well, it's a pretty ambitious plan, but anyway, let's get started. So let's start with first complex numbers. And most likely, I will dwell on, well, some of the main properties of complex numbers. I'm not gonna do everything. Probably you can imagine there are a lot of things to talk about in complex numbers. And also, I would like to talk today a bit about them, because next time when we will do geometry, next week basically, I will talk about complex numbers again, but in a different context, in geometric context, and you will see why how useful these numbers will be. Anyway, let me just say a few facts about complex numbers. You know how a complex number looks like. So it's a number of this form, a plus bi, where a, b are complex numbers, right? And this guy, well, I would like b to be different than 0, but you can include the real numbers as well. But this guy I has this property that
real quick, what does that say? A and B in C? Is that?
Yes, complex numbers. This is C. This is a set of
A and B be real numbers?
Oh my goodness, yes, A, B are real numbers, sorry. Yeah. This is the set of complex numbers. Yeah, A, B are real numbers, such that, and this guy I square will give you -1, right? This is what we call the purely imaginary. All right, you can also, well, you can play around here and you can say that the absolute value of this will be nothing else than just a squared plus b squared, right? This will be a non-negative real number always. And of course, you can, this is the algebraic form. Right? But you can also have the geometric form of a complex number. Let's say you can write this in this way. Usually, this is denoted. Let me be specific here. Z equals R, and this is so the trigonometric form will be cosine R cosine of phi plus I sine of phi, right? So this is where R is the one above, right? Well, this is the trigonometric form. Also, there is another form, and anyway, I'll discuss the properties of these numbers. There is another form where, for example, well, in the case of, you also can use this form, e to the I, let's say, phi is cosine phi plus I sine phi. This is the Euler form. right? For a complex number. So you can represent it in this exponential way. Well, this is Euler's formula, which connects the trigonometric functions with exponential functions via complex numbers. That's exactly what it does. And of course, as you can see, I wrote it here for, well, I assume that R is, this complex number is of, has absolute value equal 1. Well, now you can using Euler's formula, we can represent, we can write cosine of, we can write cosine and sine in terms of the exponentials, right? In terms of e to the I phi and e to the negative I phi, let's say, right? For example. So we will have the following formulas, and I'm just going to tell them directly. This will be that cosine of phi, let's say, okay, let's keep the denotation, cosine of phi is e to the I phi plus e to the negative I phi, everything over 2, right? Right? Where you can say that cosine of phi is the real part of e to the I phi. And then the sine of phi can also be expressed in the almost in the same way. This will be e to the I phi minus e to the negative I phi, everything over 2i. And again, this sine of phi will be the imaginary of e to the I phi. So these are the formulas. Right? And also there are plenty of things to talk about. Well, for example, so I want you to look at these formulas. So keep them in mind, because they might be very, very useful when we will use them in solving some problems, even involving polynomials and so on. There are some other things useful about complex numbers, right? For example, keeping in mind Euler's formula, so remark, so let's look again at Euler's formula. Let me, right? Keeping in mind Euler's formula, one, we can do the following. For example, if I have, if I want to compute the exponential e to the z, and this is a plus ib, right? E to the power a plus ib, right? This will be nothing else than e to the power a times e to the power ib, and this will give us, if I want to use Euler's formula, it will be nothing else than e to the a times what? Times cosine of b plus I sine of b. So you can express the exponential of a complex number, which is great. Now, I would like to talk also about another thing, which I haven't mentioned, but I should have mentioned it. What a very important thing is for the trigonometric form is what we call the Moivre formula. So another, maybe I should have mentioned it here. Anyway, the Moivre formula, which basically says the following. Well, it says that cosine of phi plus I sine of phi, everything, if we raise this everything to the power n, this is nothing else than just cosine of n phi plus I sine n phi. That's the Moivre formula. So you have a complex number, you raise it to the power n, and trigonometric form, you'll get this. And anyway, you will see when we deal with a problem, we can use this kind of formulas. The proof of this, I'm not going to go into the proof of these because that's not the purpose of our class. Well, you can just use induction. So I'll leave it to you as an exercise if you want. There's the proof, use induction to prove this. And some trigonometric formulas, right? All right, that's one thing that I wanted to mention. Now, I would like to say another thing, some other useful facts about complex numbers. For example, so some other useful facts. For example, if I would like to, so we have the following formula. One can show, and I will leave it to you as an exercise, the following formula. Okay. Well, if we take the absolute value, and I'm going to write it in exponential form of 1 minus e to the negative I phi, right? This guy, this will be nothing else, and I'll leave it to you as an exercise to show that this is nothing else than the absolute value 2 sine of phi over 2. Anyway, this will be exercise for you to complete the details, but this is a formula, an important formula, which kind of connects the exponential form to the trigonometric form. Anyway, now I want to talk about something else as well. I want to say a few words about roots of unity, because these are very important. And we will use these roots of unity even when we deal with polynomials as well. Well, the roots of unity basically says that given a positive integer n, right? The complex numbers that satisfy this equation z to the power, the complex numbers z, okay, that satisfy z to the power n equals 1 are called roots of unity. Right? So these are the roots of unity. Well, you'll see them, we'll denote these by and we denote them by, well, 1 epsilon squared all the way up to epsilon to the power n minus 1, where this epsilon is cosine of 2 pi over n plus I sine of 2 pi over n, right? Or if you want, this is in, you can write them in trigonometric form, or this epsilon, well, I should put here epsilon n, so the right, or maybe I should put them, anyway, you understand what I mean. Or you can write them in the following way. Let's put here epsilon k. You can write this in the exponential form, which would be e to the 2 pi I k over n. Right? It's the same thing. So either way, you can identify, it doesn't really matter that much. And also, why are these important? They're important because you can use these roots of unity. Well, they're important for many other things. You'll see that this will be the affixes of next time of the regular n-gon, when we'll talk about, when we will see their applications in geometry. But also from the algebraic point of view, these are very important for factorization of polynomials, and especially roots of unity are important for the factorization of the polynomial, since we're going to talk about the polynomials today, z to the power n minus 1, right? And guess what? If we denote, if epsilon, like I said, this is e to the 2 pi I over n, right? Then guess what? Is b the, is the first n root of unity. Then we will have the following factorization. Then z to the power n minus 1 will be nothing else than just the product for k equals 0 to n, right, of z minus epsilon to the power k, right, which is nothing else than just z minus 1, z minus epsilon times z minus epsilon to the power n minus 1. So here it goes to n minus 1. So this is how we can factorize a polynomial. Keep this in mind, right? And also you can factorize it using the geometric series, but you can also identify these with complex numbers. Okay, well, these are the basically, well, in a nutshell, the most important things. Probably I missed some of them, but I don't want to lose too much time with these because I want to stick to applications most. And there was a problem, let me check in the list here. There was a problem last time which I didn't have time to cover, which says the following. So problem. This was a Putnam B2, 1973. I've done this a couple of times, but anyway, I can do it we can do it again, which says the following. Let z be be x plus yi be a complex number with x and y rational numbers. And with the absolute value of z equals 1. Show that the number this number, the absolute value of z to the power 2n minus 1, is rational for every positive integer n. For every positive integer n. Okay, so that was a problem, right? Anyway, so let's look at it. Some of you already have solved this, but based on everything we have right now, well, we can do this in many ways. We can use the algebraic form, we can use the trigonometric form, we can use even the Euler form. So there are plenty of ways to attack this. And in fact, probably that's what we're going to do. But I want you to look at it for a couple of minutes before we dive into the problem. And In fact, I'm thinking of showing you three approaches to this problem. That's why I wanted to do it, because you can see how we can attack this problem by using the algebraic, writing the complex number in its algebraic form. Then we can do it using trigonometric form, and why not using Euler's form. And you'll see they're basically the same thing, but it's just a little bit well, different notation. But I want you to look at it for a couple of minutes. All right, let's see. So now let's use the algebraic approach, let's say. Basically, I'm just looking at this problem. I'm just going to use, well, only the algebraic form of a complex number. So I'm not going to do anything fancy with cosine and sines or whatever, exponentials and stuff like that. So let's see. What should we do first? Well, I can denote this by, well, you can prove this by induction. Show that, well, if we look at this complex number and we raise it to the power n, right? This at some point will look like this, 2a plus bi, right? With a and b are rational numbers, and a squared plus b squared equals 1. So one can show this, right? It's an induction. Right, we can even denote this by W if you want. Or if you want, you can even write, well, when you, well, it's easy to see this. Anyway, it will be easier for you to see it when we write this in this complex number in Euler's form, when we write it as a exponential, but anyway, let's stick to this. And now, what we're going to do is the following. We're just going to compute this guy, z to the power 2n minus 1. And once we do this, well, we'll get the following. This will be nothing else than just a plus bi squared minus 1. And if you do all this algebra here, and then we can do it, this will be a squared plus 2ab squared plus bi squared, right? Minus 1. And this will be equal to a squared minus 2ab minus b squared, right? Minus 1. But wait a second. And this guy, if we use the fact that a squared plus b squared equals 1, right? It will give us what? Sorry, here I have, this is not a square here, I'm sorry. This is just I. Okay. And now this will give us what? This will give us 2abi, right, minus 2b squared, right? And here we use the fact that a squared plus b squared equals 1. All right, so at this point we know this. Now, again, this is a complex number. Let me write it in the negative 2b squared plus 2ab times I, right? Z to the 2n minus 1, it's written in this way, as you can see here. All right, great. And now the only thing we need to do is just to take the absolute value. So this implies that the absolute value of z to the 2n minus 1 will be equal to what? To the absolute value of this number. Anyway, I'm not going to call it with another letter. I'm just going to use it like in the way it is. 2b squared plus 2ab times I. And this will be equal to what? If you compute this, will be equal to what? Can you tell me? So it's the absolute value of a complex number, right? These are, if you look here, this is the, let's say an x, this is an y. So it will be what? The square root of each one squared, right? Or if you want, you can even have another option here, if you look at it, since we don't want to do too many computations, we can actually factor something here. So you'll have, let's say you can factor 2b. So you have 2b times, what do you have? AI minus b plus a times I, right? And now it's quite clear what to do. This will be the absolute value of 2b times the absolute value of negative b plus ai. Well, in this case, it's which is 2 absolute value of b times what? This guy will also have the same absolute value, right? It will be the square root of a squared plus b squared. But this guy, you know, it's 1. So this will be 2 absolute value of b. But you know that this guy, a and b are, if you look here, these are rational numbers. So this is again a rational number. That's it. It wasn't a big deal, right? So that's the algebraic approach. As you can see, we dive in directly into the problem. It's just computations, nothing else. But now let's use the trigonometric approach. As you can see, so solution 1, let's say. Trigonometric approach. So I want you, this is a good problem for you to see all 3 approaches. All right, so now let's see the trigonometric approach. Well, in this case, let z be cosine of phi plus I sine of phi, right? So this is the complex number. And well, it's quite clear and you know that the absolute value of z is 1. So by De Moivre's formula, what do we have? We have that z to the power 2n will be what? Will be cosine of 2n phi plus I sine of 2n phi, correct? And now we're going to take the absolute value, and we have that z to the 2n minus 1. The absolute value of this will be what? And now let's be quite careful here. Once we do the computations, because this will be, let's see. So this will be, okay, so 2 cosine of and 2 So we will get what? So this will be -1. So it'll be cosine of 2n phi -1 squared. So it will be 2 cosine n phi, right? Cosine squared of n phi, right? Let's see. In fact, 2 cosine. In fact, you know what? Let me 2 cosine of 2n cosine. Because the computations will be similar, so it will be 2 cosine squared. Okay. So it will be, well, at some point, anyway, I'm just gonna say directly because I don't wanna, so at some point, so leave this to you as an exercise here. At some point, I'll get something very similar to the algebraic approach. So this will be something of 2, the absolute value of 2 sine of n phi, an absolute value, right? Times, and here I'll have something that will look like this, negative sine of phi plus I cosine of phi. But this guy here will be 1 because it's the same thing as the absolute value of this guy is 1 as well. Because, right? Anyway, so this guy will be nothing else than just 2 absolute value of sine of n phi. Okay, that's what we get, right? And now from here, we have to show that this is a rational number. That's what we have to show. So how are we going to show this? Well, one can use the induction. For example, we said at the beginning that we have to show this is irrational when cosine of phi and sine of phi are both rational numbers, right? Okay. Well, for this one can use, so for, and I'll leave it to you because I said it at the beginning, for n greater or equal than 0, one can use that x plus I y to the power n is nothing else than just this, what we said at the beginning, it's an a plus bi, right? For, let's say, x equals cosine of phi and y is sine of phi, right? So this is what and you can do this by just a mathematical induction, right? Okay, and for the case when n is less than 0, we can use the fact that cosine or sine, let's say sine of, because we're talking about sine here, sine of negative phi is nothing else than just sine of phi. So there is no problem, right? Anyway, as you can see, basically it's the same thing. The only difference is that I wrote this in a trigonometric form. And now the third approach, we can write this in Euler's form. And what we're going to do is the following. So let's write z. So we write z as e to the, let's say, to the I phi, right? And this guy, right? Well, again, by an induction, we have that z to the power n, this guy will be some number, let's say a plus bi, again, with a, b rational numbers and a squared plus b squared equals 1. And again, when we compute, the same computations hold true. The same computation will give us that, well, let me denote this by w, let's say, will give us that the absolute value w squared minus 1 will be, again, 2 times absolute value of b, right? Something like this. Anyway, or if you're right, this is 2 sine of n phi. And it's the same thing. So leave it to you. So you see, you can approach these problems in 3 ways. It doesn't matter how you write it. The only thing that matters is that at the end of the day, you will get the exact same computation. Okay, I want to veer towards something else since I'm on a run now. I want to talk a bit about induction. So this is the second part of this induction, and this is the first part, complex numbers. Anyway, you will see more of these applications of complex numbers once we talk about geometry next time. Again, I'm going to be on the run as well next time, since I want to talk about basically everything in geometry, well, as much as I can. Now, regarding induction, well, you know what induction is, since you know the typical induction. But also there is this weak induction. Principle, which basically says that when we want to prove that let's say weak form, anyway, weak induction principle, which basically says that if we want to show that the first step is, so let's suppose we have a proposition P of n is, you want to show that P of n is true for all n greater or equal than n0. So that's your proposition, right? So you first verify step 1, P of n0 is true. And then step 2, the implication is P of n true, right? Implies that P of, well, you can say that P of n plus 1 true for all n greater or equal than n0, right? So the next one, that's the weak induction principle, right? So for all n greater or equal than n not, P of n true implies P of n plus 1 true. But also there is a strong induction principle, and especially we will use this when we're trying to prove something about sequences. Strong induction principle. And I will use this induction when I will talk about sequences, especially when I've tried to prove something about a sequence that is positive, then, or maybe I want to prove something about a sequence being increasing, decreasing, and so on. Anyway, This is the weak form. The strong form will be a little bit different because here in the strong form is the following. So I'm giving a proposition. So again, I want to prove that P of n is true for all n greater than n0, right? That's what I want to prove. And the step one is the following. So basically, I'm verifying this for P of n0 is true, right? And step two will be a little bit different. Well, I don't want to write it in like in great detail with notations. Basically, it says that all these P of n0, P of n1, n0 plus 1, and so on, P of all the way to, let's say, P of n are true, then this implies that P of n plus 1 is true for all n greater or equal than n0. Anyway, and now you get the idea. Let me show you some examples. Like I said, there are plenty of examples of using induction, but I want to show you examples of each one of them. For example, the first example I have in mind is the Catalans Identity. Since this is a very nice application of induction, which says the following: show that 1 minus 1/2 plus 1/3 minus 1/4, and we keep going, plus 1 over 2n minus 1 minus 1 over 2n. As you can see, this alternates. This is nothing else than just 1 over n plus 1 plus 1 over n plus 2 plus 1 over 2n for all n greater or equal than 1, right? For all positive integers. Right, this is my proposition P of n. So let me put it here. And I want to show this. Right? Okay. Now we, for n equals 1, so the step 1. For n equals 1, what do we have? Well, let's plug it in. For n equals 1, I have on the left-hand side, I have 1 minus 1/2, right? And on the right-hand side, I have 1 over 1 plus 1, which is 1/2. Well, 1 minus 1/2 is 1/2, which indeed this is true. Now, we assume that P of n is true, and we show that P of n plus 1 is true. Well, let's P of n, let's write them again. P of n is this guy, 1 minus 1/2 plus 1/3 minus 1/4, and we keep going, plus 1 over 2n minus 1 minus 1 over 2n. This is this 1 over 2n plus 2 plus all the way to 1 over 2n. So this is for all n greater or equal than 1. So we assume this, and we show that P of n plus 1 is true. P of n plus 1, I want you to be very, very careful here, right? Who P of n plus 1 is. So again, a 1 minus 1/2 plus 1/3 minus 1/4. And I'm going all the way, let's write these terms here, 2n minus 1 minus 2n. And now let's see, plus. If I put here n plus 1, I will get what? This will be 1 over 2n plus 1, right? minus 1 over 2n plus 2, right? Plus 1 over 2n plus 1 minus 1 over 2n plus 2. Okay, and here on this, if I replace n by n plus 1, pay attention, it starts from 1 over n plus 2 plus 1 over n plus 3 plus, I'm going all the way, plus 1 over 2n, and it's going all the way to 1 over 2n plus 2, but it's missing, since they're consecutive, I also have to add this guy here. As you can see, I have some extra terms here. I have these two extra terms, right? And also, if you look here, I have also these two guys here. But it's missing one of them here. 1 over n plus 1 is missing. Right? This guy is missing. Well, since this guy is missing, no problem, we can add the guy. So now, what do we know? I want you to look carefully at these two. So let's see. By the induction hypothesis, what do we know? We know that this guy here, if you look, this guy all the way here is equals to this guy, right? We know this. So we know that, let's write it. We know that what? That 1 over, so let's replace 1 over n plus 1 plus 1 over n plus 2 plus all the way 1 over 2n plus, right? And now I'm gonna add and subtract that 1 over n plus 1, which is missing, right? So I have 1 over 2n plus 1, right? In fact, wait. Let me look at the right-hand side. I think that's better. So we know that this guy plus 1 over 2n plus 2. And now I'm going to subtract minus 1 over n plus 1, right? Because this is the right-hand side. This guy equals 1 minus 1/2 plus 1/3 minus 1/4 plus 1 over 2n minus 1 plus minus 1 over 2n, right? So this is the induction hypothesis. Okay, and I have these extra 3 terms here, plus 1 over 2n plus 1 plus 1 over 2n plus 2 minus 1 over n plus 1. Okay, so keep in mind that here I use the induction hypothesis. This guy here is the same as this guy here. These two are equal. So I have these extra three terms here. Okay, no problem. So this will be equal to, let's see. Well, as you can see here, what does this give us? If you look, this will give us nothing else than just what? If you look at it. Does it give us 1 minus 1/2 plus 1/3 minus 1/4 plus 1 over 2n minus 1 minus 1 over 2n, right? Plus 1 over 2n plus 1 plus 1 over minus 1 over 2n plus 2, right? Right, if we combine these two here. Right? Okay, which is exactly what we wanted to prove. What we wanted to prove. What we wanted to get, exactly. Right? It's exactly P of n plus 1. Well, that's it. End of story. So P of n true implies P of n plus 1 true. So P of n is true for all n. Greater or equal than 1. Okay, so this was an easy application. There are plenty of other applications. You can even use, you can prove Cauchy-Schwarz inequality, you can prove AMGM inequality, and so on. Now, I would like to, well, since I don't have too much time left, I want to veer towards polynomials at this point. And so the third part, fortunately, I have to run like through this material, polynomials. And this is a very important part of this lecture. And well, a polynomial, basically, it's something that looks like this. An x to the n plus an minus 1 x to the n minus 1 plus a1x plus a0. With these guys, a0, a1, an are coefficients. Are called coefficients, and usually they're complex numbers, let's say. It doesn't matter, they can be real numbers as well. And as you know, the degree of P is n. This is the degree of P, of our polynomial P, right? There are some properties of the degree. And I would like to mention two of them, which are very, very important. The first one is that the degree, if we add two polynomials, the degree of P plus, we add or subtract two polynomials, this is less or equal than the maximum between degree of P and the degree of Q. Also, another important property is that if the degree of P, the product, is nothing else than just the sum of the degrees. Degree of Q, right? And also, there is another thing you need to know. There is a division algorithm for polynomials, which says that which you already know from those of you who have taken algebra, that, well, given two polynomials, let's say P and Q, right? And which Q, let's say, is not a zero polynomial, then there are unique polynomials let's say R and S, right? Such that we can write P in the following way. P is Q times R plus S, with, of course, the degree of s less than the degree of q. Right? And you can divide polynomials in this way. Anyway, I'm not going to go into details about this. Also, another thing about this, important in polynomials are the zeros of polynomials. There are so many things to cover here, but I'm just going to cover the basics. You already know the quadratic polynomials. You know what are the zeros of this, and so on. Well, I would like to say a few things about zeros. So we say that a zero, so alpha, a complex number, is a zero for p if p of alpha is zero, right? That's what a zero of a polynomial is. And also, there exists this formulas, Viet's formulas for polynomials, which relate the coefficients. So the question is, how do we relate the coefficients with the zeros of polynomials? That is the question. And the answer is given by the following formulas, Viet's relations. And I'll explain immediately what this is all about. These are very, very important formulas. And I'm going to say it directly. If, let's say, x1, x2, xn are zeros of a polynomial, let's say p of x is an x to the n plus an minus 1 x to the n minus 1 plus a1x plus a0, right? And we can write this. There is also a way of writing this is x minus x1 times x minus x2 times x minus xn, right? Then, well, if you multiply here and you equate the coefficients, then we have the following relation. And I'm going to write it with red. I want you to look very carefully. The first will be the sum of the roots, x1 plus x. Well, of course, if I have a polynomial of degree n, it will have n roots. So this will be nothing else than just negative a sub n minus 1 over a sub n. Then I will write, let's write the second one, x1, x2 plus x1, x3 plus, and we keep going, xn minus 1, xn. This will be a sub n minus 1 over a sub n. And then we keep going until the last one, which will be nothing else than the product, which will be nothing else than just negative 1 to the power n times a0 over an. So these are the Viet relationships that you need to know, right? And I'll show you maybe a couple of applications of these. You'll see how some of them are Putnam problems. And for you to see this, let me give you the example, a particular case. When n equals 2. We have this quadratic polynomial, which is ax squared. Let me write it in this way, plus bx plus c, right? This is the quadratic polynomial. Well, and the Viet relations in this case, if x1 and x2 are roots, are the roots of P, right? Then we'll have the following: x1 plus x2, we will have only two of them, x1, the sum and the product, which will be negative b over a and c over a. Anyway, if you look closely, everything will fit into the picture here. You just take n equals 2 and you will see that you'll find exactly these. And you can play with these for n equals 3, n equals 4, and so on. We'll see examples of applications of this. All right. The first problem that I have in mind, and it's one of the, so let's see some problems. Problem 1. I think this is an all Putnam problem, but well, let me see. I have it here. It was on the list. So, which says the following. Yeah, it was inspired by a Putnam problem. Anyway, it's similar. Prove that a polynomial with only real roots and all coefficients equal to plus minus 1, right? Has degree at most 3. Okay. Well, in fact, you can actually even find all these polynomials, but anyway, I'm not going to get into details of it. So this was, I think it was inspired by a Putnam problem. Anyway, let's see. So what is the trick here? I want you to look at this problem for a couple of minutes. As you can see here, I have some information about only real roots and coefficients. Look here. So if you look closely at this problem, you'll realize that, wait a second. There must be something, some kind of a Viet relations hidden somewhere there, right? So what do you think? So in other words, if we consider P of x is an x to the n plus an minus 1 x to the n minus 1 plus a1x plus a0, right? If this is my polynomial, right? And let's say the degree of P is n. We want to show that n is less or equal than 3. Keep this in mind. So how would you approach this? What kind of idea? Of course, you want to look at Viet's relationship, right? Relations, right? So the main idea is to look at Viet's relations. That's the main idea, right? Let's look back, look at them here. Maybe I should just combine the first two, because this will give me everything I need. So let's write them again. So x1 plus x2 plus xn. This is negative a n minus 1 over a n. And the second one was x1, x2 plus x1, x3 plus xn minus 1 xn, which it was equal to n minus 1 over an. So let me look at this. And if I combine this in a certain way, in other words, if you look at this, this is almost like it's missing a square here. So let's look at the following. Let's combine these two. We combine these two equalities, and we have the following. Let's see, what do we have? And I'm going to do it in this way. x1 squared plus x2 squared, in fact, that was a bit of a trick, plus xn squared. This will be nothing else than what? Well, you can write it, it's nothing else than just what? Then x1 plus x2 plus xn squared minus 2 x1, x2 plus x1, x3 plus xn minus 1 xn. That was the trick. And now we know each one of them. We have that this is the first one is what? Is an minus 1 over an squared minus 2 times an minus 2 over an, right? So we know this. But pay attention here, because we know something about in this problem. What does it say? That all coefficients are plus minus 1. So if all coefficients are plus minus 1, what is the possibility we have here? That this expression will be what? Equal to what? I want you to look very closely. There. So what is the only possibility you will have? Keep in mind that an minus 1 and an are plus minus 1, all of them. So it's in the first case will be what? Equals what? So if ai, an minus 1, and an minus 2 are in this set. So this guy will be equal to what? If we look at it. Can you tell me? It will be 3. Is it clear for everybody what I'm saying here? This is 3. Because these guys are only negative 1 and 1. So what options do you have? So this guy will be 1. And this guy will have, let's say, an minus 2 is negative 1, a is 1 will be negative 1. 1 times negative 2 will be 3. But suppose they're that both of them are 1, right? None of them is, you'll have like 1 minus 2 will be -1. This cannot be because this guy is always non-negative. Keep in mind that. So the only option we have is 3. So we have this to be equal to 3, right, by Viet's relations. But now, on the other hand, so, right, the, okay. But on the other hand now, wait, I want to, okay. What can we do? By the AMGM, we have what? We have that x squared plus x1 squared plus x2 squared plus xn squared. These are non-negative already. This will be greater or equal than n root of x1 squared, x2 squared, xn squared. But this guy here, right? This product, so we know that this is 3, but the product of this will be what? By the product square will be what? Since we know that, keep in mind that this is x1, x2, xn squared, right? The n root of this. But this guy is nothing else than just what by Viet? -1 to the n times a0 over an, and everything squared. So this guy will always be 1. So it follows that 3 is greater or equal than n, which is exactly what we wanted to prove. That's it. Is it clear for everybody, the problem? It is tricky, I agree. So again, you use the Viet relations, the first two, so that we can get some information about the sum of the squares. You can write it for using this formula, and then you use the Viet relations to show that this equals 3, and then you use the arithmetic geometric mean inequality, and then again Viet relations to show that in fact n is less or equal than 3. You can actually determine all the polynomials, but anyway, I'm not going to get into that. Another problem that I wanted to do in the remaining time, let me see. Oh, problem 2. And this was a Putnam problem. It was actually a very nice problem. Let P of z is az to the 4th bz cubed plus c times z squared plus d times z plus e, right? This is a degree 4 polynomial at this point. So this, you can write this in this way: a times z minus z1 times z minus z2 times z minus z3 times z minus z4, right? And where these guys, a, b, c, d, and e, are integers, right? A is different than 0. And now, here we go. Show that if, in fact, z1 plus z2, these are the roots, right? Is a rational number. Right? And if z1 plus z2 is not equal to z3 plus z4, then Z1, Z2 is a rational number. Right? So this was a Putnam B4. Well, it's a little bit in 2003, I believe. Anyway, I think I'm gonna stop here because I don't want to spoil this problem for you. You can think of it, and we'll discuss it among with other problems. We'll discuss it during our recitation on Thursday. In fact, on Thursday, I'll give you some problems. Also, I'd like to talk about sequences as well, maybe induction. Anyway, I think I'm going to stop here. Thank you.